So let's first start off talking about simple microscopes. A simple microscope is a microscope that has just one magnifying lens to it. And what that means is that you simply just take one lens and you look at your specimen, very similar to that of a magnifying glass, right? Now, a magnifying glass is going to allow an object to appear 3 to 20 times larger than what its actual size is. And so it's a very simple tool that's used to allow us to enhance our view. Now, when Antoine van Leeuwenhoek worked on his simple microscope, his maximum magnification power was about 300 times the actual size of the object. So when you think about that, that's actually very, very powerful. And remember, he used kind of a series of lenses in order to view all these microorganisms that he thought were very fascinating. In the classroom and in the laboratory, when researchers and students as well as instructors are looking at bacterial organisms or other microorganisms underneath the microscope, they typically are relying on a tool known as a compound microscope. And a compound microscope contains more than one magnifying lens to it. So you've probably seen many of these in some of your previous courses that you've taken at the college. But these particular microscopes are fitted with a series of different lenses. So if you look here, we'll start first with the ocular lenses. You have two ocular lenses that you look through using your own eyes in order to see the specimens that sit on this platform. And this platform here is known as the mechanical stage. But between the ocular lenses and the platform, or the mechanical stage, you also have a set of other lenses. And these lenses are called the objective lenses. And each objective lens has a different magnification property to it. Most of these compound microscopes will have a 4x objective lens, a 10x objective lens, a 40x objective lens, and a 100x objective lens. And what that means is that the resolving power of these objective lenses each has a specific capacity to them. So if you are working with a microscope and you flip to the 4x power, that means that you're going to see the specimen that's sitting on your mechanical stage up to a power of 4 times, or 4 times its original size. And what you have to account for is also the magnification of the ocular lens. And in most instances, these compound microscopes will have a 10x ocular lens. So to figure out the total magnification, you would need to do whatever the magnification of the objective lens is times the magnification of the magnification of the ocular lens. So say you're looking at bacteria using a 4x power. You do 4 times the magnification of the ocular lenses, which is 10, and that would give you a total magnification of 40x, which means the specimen on your mechanical stage is going to be 40 times its original size. Now, even if you looked at bacteria on just using a 4x power, you aren't likely to see the bacteria, because bacteria for us, remember, are measured as 1 micrometer, and for us to be able to view them, we have to magnify the bacteria 1,000 times. So we use a special lens that's called an oil immersion lens, and it has a typical power of about 100 magnification, or 100x. So when we view the bacteria that sit on this mechanical stage using our 100x power, we multiply that 100x times the magnification of the oculars, which is 10, and that gives us a total magnification of 1000x. Again, allowing us to view bacteria 1,000 times greater than what its original size is. And that's what's really great about these light compound microscopes, is that they're able to do that because of the compound nature of the lenses. You don't just have one lens, which is a 10x, you also have these different objective lenses. Excuse me. And so you also have a number of other lenses that are fitted inside this microscope to help allow the light to bend in order to view the microbial specimens that we hope to observe. So again, kind of the key caveats here are that the compound light microscopes typically magnify objects up to about 1,000 times their normal or actual size. One thing to note is that the resolving power of a compound light microscope is about 0.2 micrometers, and this is essentially 1,000 times better than the resolving power of the unaided human eye. Remember, with our human eye, we are looking at resolving powers of about 0.2 millimeters. So this is much more effective to allow us to visualize all the different most of the different organisms out there that are either bacteria organisms or are protist organisms. Now, the compound light microscope operates on the use of a light in order for us to view anything. So without a light source, you're not going to see any bacteria or any protist organisms that are sitting on your slide that sits above your mechanical stage. The wavelength of visible light is going to measure 0.45 micrometers. And the wavelength of the visible light is going to basically limit the size of objects that can be seen, because the way that we observe objects using the microscope is we essentially manipulate light as it's passing through the specimen. So if you look down here on this microscope, this is called the illuminator, where it says lamp. Lamp, illuminator, those are the same things. But essentially you have a light source, and that light source is going to pass through the middle of this mechanical stage, and as it passes through, it's going to pass through something that's called the condenser. The condenser is going to help to focus the light up through the specimen, which there's no specimen on this particular slide, but most of you have seen a microscope slide with a specimen situated on it or affixed to it. I'm hoping that you have. But say, for instance, we want to view some Staphylococcus bacteria, and they're fixed on a slide. We'd place that slide here between these two stage clips, these two metal stage clips, and that light would pass through the condenser up into the objective lens that we have set here. And once the light passes through the objective lens, it's also going to pass through what's called the body tube, where it says trinocular head. There's lenses in here that are referred to as the body tube. And then that light is going to pass through the oculars and go into your eyes. And so as that light's passing through, it's going to essentially send a signal to your eyes and display to your eyes an image of your specimen that you're viewing underneath the microscope. So most of these lenses are especially beneficial to allow us to visualize the bacteria that's going to be situated in the slide that we're interested in. But we can't visualize anything if we don't have a wave of light that's going to shoot through the specimen and focus it into our own eyes through all of these structures in the microscope, allowing us to make the specimen visible. Now this is important. If objects are smaller than half of the wavelength of visible light, which is 0.5 micrometers, essentially, then we're not going to be able to view them using a compound light microscope. Remember, we'd have to use more specialized microscopes. And remember, for most bacterial organisms, we have to have a kind of width or a length of about 1 micrometer. So anything less than 0.45 micrometers isn't going to be able to be viewed using the compound light microscope. So let's talk about when we view specimens, we always want to make sure we know what the total magnification is, because you just wouldn't want to say what the magnification is for the power objective that you're using. Say it was 4x, 10x, or 40x. You have to include the magnification of the ocular lenses, which in most cases is going to be 10x. So when we talk about total magnification, we're talking about all the magnification of all of the lenses involved in allowing us to view the specimen. And to find this magnification, we simply multiply the magnifying power of the ocular lens by the magnifying power of the objective lens that's used. So on the lowest power of a compound light microscope, we have a 40x objective. And again, let me point out where the objective lenses are here. These little node-looking things where it says objective. There's 4 fitted to a compound light microscope. And those 4 are the 4x objective lens, 10x objective lens, 40x objective lens, and then 100x objective lens. So to find the total magnification of these lenses, you simply multiply the power of the objective lens times the ocular lens. And as I said, in most cases, the ocular lenses are going to be 10. So if you're using the 4x power, your total magnification would be 40x. If you're using the 10x power, your total magnification would be 100x. Now, when we view bacteria, we typically want to view it on the highest power for maximization of optimal maximization of to allow us to view the bacteria. So we use the 100x objective lens and we multiply that by the 10 ocular, and that gives us a total magnification of 1000x. And so as technology has improved over time, a lot of the microscopes now are being built by many of the primary companies out there that also are used to create things like cameras. So there are companies like Nikon and companies like Olympus, which typically you know them to produce camera products very similar to what you would buy at Best Buy, but they have also kind of tapped into this microscope market, and they are producing microscopes which have recording capabilities on it, which is really great for a scientist to use, because then you can produce what's called photomicrographs, where you essentially have a microscope that can be hooked up to a computer that allows the researcher to take pictures of the bacteria that he or she is viewing under the microscope. So this is a really handy dandy tool to help us further understand and capture those specimens that we're viewing and are interested in studying further. So here's a kind of an image here that you can see of a image that was digitally recorded using a microscope. One of the things that's real important to understand about the compound microscopes is that it uses a very bright field, which is essentially all this white space, in order for us to visualize the bacterial cells that exist on our slides. And so for this reason, we can also refer to as compound microscopes as bright field microscopes, because they use a bright field or a bright background to illuminate the bacteria or any of the microscopic components that we're going to be interested in viewing. Now, there's a structure on the microscope that's known as a condenser, and the condenser is a part of the scope, like I said, which can be used to focus the light. But this particular structure can be easily manipulated on the microscope, and when it is manipulated, you can change it out and put in what's called a dark field condenser. And so what this does is, instead of creating this bright field effect where all of the light is passing through all the bright areas along the slide, this adds a filter to it, which causes the objects to be illuminated and are going to be observed on a dark background. Okay, so you can kind of visualize this as being a dark background image, but you can still see these structures that are highlighted. And here's an image down here that would depict what you would see in the dark field microscope. Okay, so all these squiggly little structures, these are some spirillum bacteria that you see. And notice how the field in the background is all blocked out or provides a dark field. And so this image here is taken from a dark field microscope, whereas this image here is taken from a light field microscope. And again, that has to do with the background imaging that you see.